Okay, so let's get started. So first of all, welcome back from spring break. I hope everyone had a good break. Okay, so let me refresh your memory about some things that are due soon. So there is a lablet due, I think, soon, right? I don't forget the date, but it's due, I think, this week. And Wednesday, okay, due in 2 days. And then there is a lab due, which, and as I mentioned, every 27th of the month, there's a lab due, right? So 27th of March, there's going to be a lab, and 27th of April, there is going to be the last lab. So 1 week for the lab, 2 days for the lablet. Okay? So make sure you stay on top of things. If you have questions about the lablet labs, we are here for office hours. We are available on Piazza. Okay? So make sure you ask whatever questions you need to get a good lab. Okay? We also handed back lab 1. You probably saw the grades on Gradescope. By and large, I think the class has done well, which is generally the case. I think labs, I think students put in the effort, so it shows in terms of the grades. A few comments that I wanted to make. First of all, I think there were few of you who lost odd points for not commenting your code. Very simple things. If you look at the end of every lab, there's a rubric that shows what the points are for. Read that and make sure you address those things. I mean, it's very straightforward to know what is expected. It's in the rubric. Make sure your lab submission confirms to that. That way you will not lose points for, not putting in comments or some small thing like that after writing all the code. Okay, so that's one. The other thing that I think some of the labs had issues with threading and concurrency. So it's something that if you are one of those who lost points on either thread pool or some concurrency issue, go back and review that material. It's important to know these concepts. Okay? You go out, take up a job somewhere. If you happen to work on any large systems, they will have these concurrency concepts and they will have locking and all of this in there. You may or may not actually write the code, but it's good that you understand how to do it. That way you will understand how larger systems work. So it's a simple lab, but it has an important concept in it that you should keep in mind. Okay? So if you didn't fully understand what you were supposed to do, review the material from the lecture. Some of it was based on undergraduate concepts on threading and so on. Go review that material. Not very hard to understand if you put in a little effort. Okay? Beyond that, I think most of the labs, I think, were all fine. The average score was 88, I think. So that's pretty good. Okay. So use the feedback to do better for lab 2. Right. So if you lost some points here and there, you know what to do next time, so you can make up for that. Right. So with that, I'm going to start the lecture where we left off last time. Okay, we were talking about migration. Okay, I covered process migration, code migration already. We were talking about virtual machine migration. I'm going to do a quick recap of what we talked about last time when we ended the class, which was live virtual machine migration. Okay. So what is virtual machine migration? It's a concept that allows VMs to be moved from one physical machine to another. Okay. When a VM moves, okay, all of what is running inside the VM will also move with it. This includes the operating system, all the processes that are running inside that virtual machine. Everything is going to move along with the VM. Right? Now, virtual machine migration can be done in 2 ways. The one that is more common, which incurs less downtime, is called live virtual machine migration or live migration. Okay? In live migration, the migration happens as the VM executes. Okay? So all the applications are continuing to run, and then the VM just moves from one machine to the other. And once the migration is complete, all the running applications just simply continue to execute, but now on a different physical machine. Okay? And the VMs, not the VMs, rather the OS and the processes don't actually know that they have been migrated because they are actually running inside a virtual machine. They don't have a direct view into the physical machine. And so all of this is actually hidden from the applications and the OS that's executing inside the VM. Okay, importantly, virtual machine migration allows you to handle network connections and open sockets and things of that sort, which you couldn't do for process migration. Because in process migration, if you had an open network socket or a TCP/IP socket, that was bound to the physical machine's IP address, and that IP address doesn't move with the process. Okay, in this case, we don't have that problem. Okay, the main reason we don't have that problem is there is an IP address for the physical machine, but there's a separate IP address for the virtual machine, which is completely different. Okay, because the VM also has an Ethernet card, remember. It's an emulated card, but it is an Ethernet device. So it has its own IP address, which is different from the physical machine's IP. So when the VM moves, you can move its IP address with it and leave the physical machine's IP address behind. Okay? Because the IP address of the VM does not change. It simply moves to another machine. Okay? All the applications that have open network connections continue to work as is. Okay? So nothing is going to change for these applications if they have open socket connection. So I went through this last time, but I'm going to do a 1-minute recap, and we are going to continue from that point on. So this is a process for live VM migration. There are two ways to do this. This is called pre-copy. Okay, in the next slide, we'll talk about another technique which is called post-copy. Both of them perform live virtual machine migration. Okay, the picture here kind of shows what is going on. I'm not going to go through all of the details, but I'll just do a quick refresher. So here is machine A. There's a VM running on that machine that's shown in that blue box. Those are the memory contents of the virtual machine. Okay, if you want to move the VM, you're going to move its entire virtual, virtual, but physical memory to another machine. Okay, so what that means is that memory has a OS running in it. It has some processes running in it. You take that entire memory contents, you move it to another machine. In this case, it's machine B. Okay, and you will do this while the processes are executed. Okay, the idea is very straightforward. You do what's called an iterative copy of memory content. Okay, so you will take this memory and copy it page by page, and then copy of each of those pages appears on machine B. Okay, and you do this while the applications are executing. So at some point you copied all of the pages over, okay, but since applications are continuing to execute, some of the memory contents that have been copied over would have changed after you copied it, because maybe the process allocated new memory, new process started, and so on. So physical memory keeps changing as processes execute. Okay, so what is on machine B is not up to date with regards to what's on machine A. Okay, so now what do? Okay, we are going to iterate, okay, and repeat that same process. Okay, but now we are not going to copy all of the memory contents. We only need to copy what has changed since the first round of copying. Okay, so the VM, when you do this copying, is going to keep track of which memory pages have been modified, okay, once they have been copied over. So it has a list of these modified pages. So it's only going to send those pages over in the next round. Okay, and presumably those pages are much fewer in number than the original set of pages. Okay, so that means that it will take less time to send those pages than the first time around you sent everything. Okay, so the process is going to keep iterating, because every time you send some pages, some more pages change. Okay, but since you are sending fewer pages, the amount of time it takes you to send those pages is less than the previous round. Okay, which also means that the number of pages that are likely to be modified is hopefully going to be less than the previous round. Okay, because let's say in 1 minute you change 100 pages, so you are modifying 100 pages a minute. Okay, the next round it only takes you 10 seconds to send the deleted pages. So you are going to have 1/10 of the pages that have changed in that time, assuming some sort of an average rate at which memory is actually changing. Right? So in each round you continue to do this, and eventually you are going to be left with a very small number of pages that have changed since the previous round. Okay? Because the time is shrinking, and so are the number of pages, hopefully. Okay? So at that point, you are going to pause the VM. Okay? You take a small pause. You copy those small number of pages. Okay? Copy the register values, because the registers also have to move, not just the memory pages. And at that point, both A and B have identical memory contents. The VM is frozen for a very short period of time on machine A. Okay? So since you have identical contents at this point, your machine has completely migrated in terms of its memory state. So you are just going to resume it on B. Okay, and just delete whatever is on A. Okay? This is basically now migrated the whole VM, including its processes, application, everything is moved. Okay? Socket connections, everything move over. Okay, there's one small detail which is actually the last step there, because here the net IP address of the VM moves with it. Okay, now whatever IP address was assigned to that blue VM, which is separate from the A's physical machine A's IP address, has now moved here. Okay, so you use what is called an R packet, which will tell the switch, the network switch, saying that that IP address is now on a different port of that switch, so that it can send the packets that are coming for that VM on a different port. And then all the packets start arriving to machine B. Everything stays as this. Okay, so that's the process. It's called pre-copy. Okay, your question.
So if the machine located the packet switch and the other network, or can the migration happen?
Okay, question is, can machine B be part of a different network, or do they have to share a switch? Okay, so there are two questions actually. There are two different answers to both. The first thing is, this process works on one cluster. You are not migrating in this process something on the internet to some completely different location. That is called wide area migration. That's a different approach. What I showed you here is called local area migration, LAN migration. Okay, so it assumes that machine A and machine B are part of the same local area network. Okay, presumably they are part of the same subnet. Okay, they don't have to be on the same switch. Okay, but they have to be on the same subnet or the same LAN, because this is going to just only work over a LAN. Okay? If you are part of a completely different address space somewhere on a WAN, you're not going to know this, because routers have to then send packets to the right place, not that the switch is simply sending packets to the right port. Okay? So it only works for local area migration. They don't have to be on the same switch, though it can be a different switch on the same LAN, it still be fine. Okay? This is the first point. Second question is, I said all the network connections are fine, but what about files which are on the disk? How do they work? You only moved memory, right? You could be accessing files. What do we do for the files? Okay, so there are two answers to this question. One is, so first of all, files are going to be stored on the virtual disk. Okay, virtual disk is itself a file which looks like a disk to the virtual machine. Okay, that's first thing you want to keep in mind. And the virtual disk is going to be a file somewhere in this network. Okay, so we can do one of two things. First is, if that entire virtual disk image is stored on a file server, not locally on this machine, but on some other server that's not shown on that picture, you can simply access those files from a different machine, because they're on a server. So long as both machines can access that file server, your files can be accessible from any machine on your LAN. So that's not a problem. Okay? So your processes will continue to access their files. It's just that the files are on a different server, so you can continue to do that. Okay? That's one option. The other option is that this virtual disk image, which has all the files, is actually local to machine A. It's not on a file server. It's on a local disk of machine A. In this case, you actually have to move the virtual disk as well, just as you moved virtual memory. Okay? So it's now a disk. It's going to take a little longer to move an entire disk image than it took you to copy a memory image. But be that as it may, okay, you can move the virtual disk to another machine, and then you can continue to access it on the new machine. Okay? And you can use the exact same pre-copy mechanism to do this, because remember, these files might also change while you're copying them over. So you'll copy the disk image page by page, and then you do repeat that until the same thing you did for memory, you can do for disk. Okay, so you can use that same mechanism. Okay, so you use one of these two techniques. The common technique is to keep all the files on a file server, so you don't have to move large amounts of data. You only move memory content. Okay, that's much faster. Okay. Yes, question. Okay, question is, given that this is all happening in a cluster, is there any restriction on hypervisors or OSs or anything like that, right? So the only restriction is that the VM should be executable on the new hypervisor. So typically, we assume that machines are running the same hypervisor. Okay? It's normally type 1, but you can do this for type 2 as well. There is no restriction on why you couldn't do this for type 2. But you assume the hypervisor is similar because the VM, its configuration files are also getting moved, and that is something that a hypervisor, it may be specific to a certain hypervisor. So that's what we will assume. We don't have any restriction on what OS is running inside the VM or anything like that. Anything can execute. Okay, is that clear? All right. Here is another approach for doing exactly what I said. Okay, this is called post-copy migration. Okay, so this is going to be a little different from what I said previously. So in this case, if you want to migrate the VM from machine A to machine B, what you are going to do, okay, is you are going to pause the VM. Okay, take a very short pause. You are going to copy the register values only to the other machine. Okay, and the register values is only small number of registers, so it's fairly quick to transfer them. Okay, and then you are going to just resume execution of the VM on the second machine with only the register values. Okay, you're not copied the memory contents at all. Okay, just copied a small number of registers and you started executing the VM. Okay, so what is going to happen? The program counter will execute the next instruction, okay, which is already in the program counter. Okay, maybe it tries to access some memory, okay, but memory hasn't been transferred, so you're immediately going to get a fault. You'll get a page fault because the page is not in memory. Okay, so then this VM is going to pause, okay, and it's going to essentially do a page fault. Try to address the page fault, and the way you are going to do this, you are going to go to the RAM on the previous machine and fetch that. Okay, because so normal page fault, the page is on disk. In virtual memory, you bring it from disk. In this case, the page fault, the page is actually on another machine, so you're just going to fetch it over the network. So one or maybe a page appeared here, so you will execute the next instruction. Maybe it accesses some other random page, causes another page fault, and then you will basically repeat this process. Okay, so in this case, you transferred the register, and memory contents are being fetched on demand as a result of page faults that the virtual machine incurs while the process is executing. Okay, the previous case, in pre-copy, you copied all the memory contents. Okay, it took you longer to do that process, but the VM was continuing to execute, and then you took a pause and then you transferred the content. In post-copy, okay, you essentially copy the memory after the migration. Okay, that's why it's called post-copy, and all of the memory contents are being transferred as a result of page faults. Of course, you can run a second process in the background that steadily fetches pages, even though they have not faulted, because eventually you want all the memory to have transferred over. Okay, so you fetch on demand plus you fetch in the background, and the two together allow you to then bring all of that memory content while the VM is now executing on a different machine. Okay, so this is called post-copy migration. So you can do either of these two. Okay, in post-copy, the problem that you are going to see is that applications performance will suffer because they will initially see a lot of page faults to bring the working set of that process into memory. Okay, into memory of machine B. Okay, so you will see a whole bunch of this page fault. Once the working set is in memory, then the process will start executing properly. But it's faster to move because you just move small. Well, I shouldn't say faster to move. The migration is immediate. Okay? You basically say migrate, and then you copy register and start executing it on the other machine. You don't wait for all the memory contents to have transferred over before you start executing. Is this clear? Okay. So there are pros and cons of either of these approaches. Here is a picture that shows your time line of how things are going to be done. That top above the blue line is the pre-copy, below is post-copy, Okay, so in pre-copy, you'll see that when you start the migration at the when it's green, then you have round 1, round 2, round n. Okay, and then you copy the dirty pages, okay, which is that short pause I spoke about. Okay, you copy the registers and you start. Okay, in post copy, you start the process, you do VM, you just migrate the registers, that's the state, and you restart the process. Okay, and then you asynchronously bring pages over, or you bring them as on demand if you have page faults. Okay, so these are the two techniques. What kinds of pros and cons do you see? Yes.
PostCopy, we are not as and when as much as the parent VM that will take some time after all.
Okay, so what is being said, maybe I'll paraphrase some of what you said, is in post copy, since you're fetching memory on demand, okay, it's going to take you some time to fetch each page. So the process that actually faulted when it was trying to execute and access that page will have to pause until the page is brought over. Okay, so there's going to be a performance penalty for processes, okay, while you're fetching some of these early pages. Now, what about pre-copy? There's no performance penalty, but is there a disadvantage? Yes. You have to copy the pages 3 times. Why is it 3? N times.
You have to copy multiple times. That might not be.
Okay, that's a good observation. So in post copy, each page is transferred exactly once. Okay, because the VM asks for it, it moves over and you continue to execute. Okay, in pre-copy, a page might have to transfer multiple times if it changes after it has been copied over, because there are n rounds. Okay, so the total amount of data copying in pre-copy is going to be much higher. Here, the amount of data that's transferred is equal to the memory contents, because each page is transferred exactly once. Okay, because once you transfer it, you change it on the new machine, and it has not changed on the previous machine because you stopped executing. Okay, so there's more data copying for pre-copy. Okay, page might have to transfer multiple times. Okay, and there's a small chance, okay, that pre-copy may not terminate, especially if you're badly behaved VMs. If they keep churning memory, after each round you have to transfer a huge amount of memory, so you never converge. Okay, the convergence happens if you are well behaved, which means that the average rate of dirtying pages or writing to pages is more or less not changing a lot. Okay, but if you keep changing a lot of memory contents, after each round you still have a lot more to transfer, so you may actually never terminate, or you have to take a big pause to transfer a lot of memory, in which case you will see a downtime. It won't be live. Okay, so there are some disadvantages there, but there's no performance penalty for well behaved memory accesses, which you do see in post copy. Okay, yes.
Why migrate a VM? What scenario?
Okay, why would you migrate a VM? So what scenarios would you have to do that? So we'll talk about cloud computing in just a few minutes. Okay, so suppose you have a server where some number of VMs are running, your application gets overloaded. Okay, VMs can actually allow you to increase the resources allocated to it on the fly. You can say this VM has 2 cores. Maybe the application needs more. You can actually give it 4 cores and it will now suddenly see more cores or things of that sort. So load balancing is a good reason. Okay, that's a common case. So you can move the overloaded VM onto a bigger machine, give it increase the size of the VM by giving it more RAM cores, and then it will continue to run. That's a use case. Okay, yes. Will there be more network loss in pre-copy than post-copy because the downtime is larger? So the downtime is not that large. That last round where you transfer a few pages is just a few pages. Okay, so maybe a few kilobytes are going over. Okay, on a gigabit Ethernet, that's nothing. You will only see maybe millisecond level downtimes, which is not even perceptible. Okay, so it's somewhat smaller here because you're only transferring registers. But I think in both cases, it's not really perceptible. Yeah, next question.
PostCopy, can they ever as
Okay. Question is, in PostCopy, can there be a scenario where some pages are never accessed by the process, so there's no page fault, and then you never bring them over? Okay. So to prevent exactly that scenario, there are two ways you are bringing memory contents. One is as you fault on demand, but as I said, you also have a background process that is then fetching all the remaining pages, even if they are not faulted, because you eventually want all the memory to come over. Otherwise, you cannot terminate or delete that memory, right? Because some memory is never transferred. So you will do both. Yeah, yes, question. A PostCopy or files migrated in the same manner. So you can do the same thing for files, right? So you can assume that they are on the servers and you don't move them at all. Or you can assume that the virtual disk is local to the machine, and then you can move it over either using pre-copy or post-copy. If you want to do post-copy, you can do the same thing for the disk. Exactly the same thing is going to work in both cases. Okay? But the easiest approach is to not move, keep things on a file server. Okay, so you have a question, yes.
Does the package, the ARP package happen before or after?
Okay, question is, in both of these scenarios, does the ARP packet get sent before or after the restart? So it has to be sent at the step where you are restarting the VM. Okay? It doesn't actually matter when you send it, so long as you do it exactly at the same time. A safer approach is, it doesn't really matter. You can do it just before you start or just after you start, but you have to do it around then so that all the packets will start coming to the correct VM. Okay. All right. So next is, how do we do all of this for my containers? We talked about process migration before spring break. We talked a little bit about VM migration. Now we'll talk about containers. Okay, that's OS virtualization. I remember we talked about Docker and so on. So now we are thinking about migrating containers, which is going to be much more lightweight than migrating a VM. Okay, because remember, a container only contains processes. Okay, the OS is running outside, because you are virtualizing the OS interface. So containers don't have OSs in them. VMs have OSs running in them, or one OS per VM. Containers only have applications or processes running in. So it's more lightweight to migrate a container than it's to migrate a VM. Okay? So there are many techniques to do this, and this slide actually is not specific to containers alone. All of this also applies to the VM. Okay, this just shows three techniques to migrate container or a VM. First is called cold migration. In cold migration, all you're doing is you're copying the virtual disk of that VM or a container when it's not executing. Okay, just a disk image. You copy the disk image and then you you boot up the VM. You do a cold boot, you start the VM and it starts running. Okay, so in cold migration, there are no processes moving, there's no OS moving. You actually move the disk and then you boot the VM on the new machine. And that's called cold migration. Okay? So that's cold. Then you have warm migration. In warm migration, okay, you have an executing VM, okay, and you want to move it from one machine to the other. So you do the straightforward thing and say, I'm going to pause that VM. Okay? Which means that whatever is running is paused, nothing is changing, and you just move the memory contents. Okay? Now, it's much easier to move memory contents when the VM is paused because memory is not changing and nothing is executing inside the VM. You paused it. Okay? So you move the memory contents, possibly you move the disk image if you want, and then you resume execution. Okay? This is, of course, going to incur a downtime because you do a pause and resume. Okay? But it's much easier than doing anything live because nothing is changing. So it's just you pause, you move, you resume. Okay? So you basically suspend running the VM or container. Okay? You might actually even copy the memory contents to disk, and then you move the whole thing over and then you resume. You don't even have to transfer memory. You can save it to disk and move the whole thing into a later time. Okay. When you do the virtual machine lablet, okay, you will actually be playing with virtual machine. So you can say that you can pause the VM. Okay. If what the virtual machine hypervisor does is it copies all the memory contents to disk, you can come back later, maybe a few hours, many days later, and resume, and it just starts from that point. Okay. So that's basically pause and restart. In this case, in that case, you didn't migrate, but you could have just as well have taken whatever is stored on disk, copied it to another machine, and resumed it there. Yeah, it would have migrated the VM for you. Right? So that's warm migration. Okay, and then hot or live migration we talked about already. So this is migration while the container or VM is executing. So there's no downtime that the VM should see. Okay, so there are these three techniques: hot, warm, and cold. Okay, cold basically means that the process is you are not saving any process state or anything like that. You just move the disk and you restart the VM. Okay, warm actually incurs downtime, but you do move the application processes, and hot or live means you move everything while things are executed. So these are three techniques. Okay. So we'll start with some of the other ones for containers, then we'll talk about live at the end. Okay. So before we do that, I want to introduce another concept called snapshots, because that's useful for looking at warm migration and even cold migration. Okay. So what is a snapshot? A snapshot is a general concept in operating systems and distributed systems. A snapshot simply means a point in time copy. It's a copy of something at some point in time as it existed at that time. Okay. So the general concept, it's widely applied for things like disks and virtual machines. So you can take a disk and you can make a snapshot. So that will preserve all the files on that disk as it existed at the time of the snapshot, and then you can continue to make modification. The snapshot will preserve the content from that point. So it's often used for making backups. So every night, if you do a backup, you take a snapshot, okay, and then you can copy that snapshot somewhere else, and then files can continue to change. But you now have a copy as it existed at that. So that's a backup of that. Okay, you can do the same thing for VMs and containers. You can essentially take a snapshot that preserves the memory state and the disk state of that VM as it existed at the time of the snapshot. Okay, so one thing that you can do with VMs is you can actually go and resume a VM from any previous snapshot. Okay, so this is often done if you want to roll back. So let's say you take a snapshot, then you go install something on your VM, something goes wrong. Okay, now you want to undo all of that. You can just go and say restart the VM from the previous snapshot, and then all the memory and disk contents are preserved. It will just reboot from that point on. Everything that you have done beyond that is gone. Okay, because you can roll back to a previous point. Okay, because that's what a snapshot will allow you to do. Okay, it preserves memory state and disk state. It's like a backup that has existed at a certain point in time. Okay, that's the notion of a snapshot. Now there's another concept called a virtual snapshot. Okay. A virtual snapshot is a snapshot, like any snapshot, it's a point-in-time copy, but it's a more efficient way of making a copy. Okay. It uses something called copy on write, okay, or COW, to make a snapshot. Okay. Now, if you think about it, since a snapshot requires you to make a real copy, if the memory contents are large and the disk contents are large, you have to put a lot of time. It will take a lot of time to make a copy. Maybe it's a 100 gigabyte disk image. You're going to have to copy 100 gigabyte disk image to make a copy. That might take some time. Okay. So most of these VM technologies, even file system technologies, don't actually make a copy. They make what is called a virtual copy. Okay, so it looks like a real copy, okay, but both the original version of the VM and the copy are pointing to the same set of data. Okay. And you only make a real copy when some data is actually modified by either the snapshot or the original. Okay. So you essentially do what is called lazy copying, okay, which is what copy on write means. Okay, copy on write says that you have a snapshot. Okay, let's say it's a file. Okay, you make a snapshot of that file. Okay, normally you would have to just make a copy and you have two copies. Okay, in a snapshot, in a virtual snapshot, both the original file and the snapshot will point to the same data. Okay? And only if you make modifications will you make a change. Okay, I'm going to show you a simple example. So let's say that's a file. Okay. If you make a real snapshot, you're going to make a second copy. Okay, that's the original file. That's your snapshot. Right. So these are two separate copies. You can make modifications to both of them. They're just looking like two different objects. Okay. So but that requires you to pay the overhead on making a copy of that. Okay. So now, if I make a virtual copy, this is what is going to happen. Here you have a file, and this is your snapshot. So both of them are actually pointing to the same underlying data, okay, which is the original. Okay. So now, if an application opens this file and makes a small change, okay, let's say you try to write to that location in the file, what you will do is you will basically take whatever you're changing and then you will make a copy of it. So now this snapshot will point to the old contents and this copy that you made, so that you still have you still preserved what was there previously, okay, because you're modifying the actual copy. Okay. So you only copy when something is written to the actual data. Okay. So now if you go and write to another part of the file, you will essentially take that and make a copy. Okay. So essentially you are accessing whatever is not modified, you access that data from the original. Whatever is modified, you made a copy of the old content, so you access it there. So you basically copy, is called lazy copy. Okay, you copy on demand, because if it's not changed, why bother copying? Okay, it's save space, it's less overhead. You do it lazily when something is about to change. Okay, so that's the notion of virtual snapshots, and that's an efficient way of doing snapshotting using copy on write methods. Any questions? All right. Yes. Yeah. So question is that doing periodic diffs? Is that your question? So periodic diffs are not necessarily copy on write. A copy on write is diff on demand. Right. So you will basically, if you write to a block, before you write to a block, you make the copy of that block, and then you write to that block. So now you have the old block and the new block. Okay. So now so that's what you're going to essentially do, right? So it's the same thing for any VM. If you're trying to write to a memory page, you'll make a copy of that page. So you preserve the old version of the page, and then you write, because once you write, the old version is gone, right? So you will only make copies that you need. That's what it means. Okay, different from diffs though. Okay, so it's snapshots. As a concept, you can now start thinking about how am I going to do all these migrations I talked. Right, a warm container migration, very straightforward. Okay, you want to essentially move a VM or a container in this case. You are simply going to make a snapshot. You're going to pause, make a snapshot, okay, and then you are going to copy that snapshot to another machine, and then you can even continue executing that container. It will keep changing, but you actually have a copy that you can migrate. Okay, so essentially pause container VM, container execution. Okay, you checkpoint state. Checkpoint means you take a snapshot. Okay, that you copy that to disk, okay, and then you can copy that to a different machine and you resume execution on the other machine. Very straightforward. Yes.
Copying VMs it's on the network.
Yes.
But containers.
Yes. Yeah. Question is, can you move a container where the container actually does not have necessarily an IP address associated? I'm going to come to that. Okay? Just give me a few minutes. Let's talk about this concept first, then we'll talk about networks and files. Okay? So checkpoint restore, straightforward way of doing warm migration. Okay? Using snapshots, you make a snapshot to copy to disk, and you move those contents to another machine, you restart the container. Okay, and you will do this when you do Docker and things like that. You can actually save state of Docker images, copy that somewhere else, start it on another machine. You'll just restart from where you left. Okay, so that's one approach. Yeah. Now Linux actually uses that checkpoint restore. Okay, in Linux is called CRIU, okay, which means checkpoint restore in user space. Okay, as a generic Linux mechanism that is used both for warm as well as live migration. Okay, and you can use it to do snapshots and so on. Now, CRIU works for processes as well as containers. Those containers are just a bundle of processes as far as Linux is concerned. Okay, so when you migrate a container, you're just migrating all the processes in them. So you do this process, you do the snapshotting process for each individual process. So it's going to use what is called the /proc file system in Linux. Okay, if you know what that is, that's fine. If you don't, that's also fine. What that allows you to do is it allows you to look at all the processes that are running and all of their memory contents and so on. Okay, so you will use that mechanism to save the process state, okay, file descriptors, memory state, etc. So you will save that to disk. That's your checkpoint. Okay, and then you can copy that state to another machine. Okay, so you have on another machine, you have a CRIU restorer. So it's going to use something called fork. That's a system call. It creates a blank process, not a blank process, but it creates a process, a copy of the process that called fork. And then you're going to take all of what was saved to disk, okay, and you're going to put that into that fork process that will essentially restore that process. Okay. So the way you're going to move containers is you first say what are the processes inside the container. Maybe there are 5 processes. Okay. Then you're going to go to the Linux proc file system, take the first process. So first you pause execution of the entire container. So all the processes are paused, all of those 5 processes. You look inside /proc, you take the first process, write it out to disk. Take the second one, you write its content to disk. You take the third one, do the same thing. Then all the processes are now on disk. Okay, because they are paused, it's not changing. And you copy all of them over. Okay, so you have now transferred the memory state of the processes to a new machine. On that new machine, you have to recreate that entire container. So you are going to do fork to create a new process and then take the saved content and you just insert them into that process. Okay, and then all your processes have been recreated on another machine. Okay, so that's what you're going to do. Okay, now we have to answer the question that was asking what happens to network sockets. Okay, because in virtual machines, okay, there was an IP address associated with the VM that could move when the VM moved. Okay, if you're moving processes don't have IP addresses. If a process has open socket connection, you just move to another machine, that socket connection will break. Okay, that's the way it is. Okay, now so if you migrate an individual process using CRIU, not a container but a process, and it has socket connections, then it's the same problem as any other process migration we've been talking about. We said that simply doesn't work because the new machine has a different IP address. So you can't just move it and expect your socket connections to work as is. Okay, so that's not going to work. Okay, but if those processes are inside a container, okay, you can actually make this work, because although containers are just a bundle of processes, you can also assign an IP address to a container. Okay, that functionality exists just as you can assign an IP address to a VM. Okay, most operating systems will also allow you to assign a separate IP address to a container. If you do that, then you can move the container's IP address with it. Okay, in that case, and that case only, will your network connections move with you. But if you move individual processes with CRIU, it's not going to work. Is that clear? So typically, I should also say, typically when you create a container, not necessarily going to get an IP address, but in most cases it will. So when you are doing your Docker assignment, you can actually log into your Docker image and look for its IP address, and you will see that its IP address is different from the IP address of the physical host. Okay, because Docker created a specific network interface and gave that container its own IP address. So in these cases, you can actually move the containers because the processes are seeing the container's IP address, not the physical machine's IP address. Okay, is that clear? Okay, so that's CRIU. And one last slide here, then we are going to switch to cloud computing. The slide is on viruses and malware and things of that sort. So it's unfortunate that the most prevalent case of code migration is for bad purposes, which is to spread viruses. Okay, viruses and malware are an example of code migrating from one machine to another. It's self-replicating. Okay, it basically moves from one machine to another, often to find some exploit, which is why it's moving there, and then it does bad stuff and whatnot. So there are all kinds of ways you can study this. We talked about sender initiated, receiver initiated, and so on. So virus is sender initiated because the sender, which is the virus itself, is moving to another machine. It's replicating the code, executing on another machine, and continues to do that. Okay, so that's your autonomous code. Okay, receiver initiated is different, where you get a phishing attack or some such thing. You click on a link that downloads some malware onto your machine, and then your machine gets compromised. Okay, it's just an example of code migration, not the one that we really want to write ourselves, but something to keep in mind. Okay, so I'm not going to say much else about viruses, but I just wanted you to keep this in mind. I'm going to actually switch gears and start the topic of cloud computing. Okay, so we won't be able to finish all of this material today, but we will start and maybe we'll end in part 2. So part 1 is data centers. Part 2 is actual cloud computing. Part 3 is Kubernetes orchestration and things of that sort. Okay, so you had a lecture on sustainable computing some time ago before the first exam, and at that point you had actually at least heard of a data center. I'm going to reintroduce that concept, then we'll use that to understand what cloud computing means. Okay, so what are data centers? A data center is simply a large facility where you can host a number of servers, large number of servers, lots of storage, and run all kinds of applications on it. Okay, so the terminology that's often used is called a server farm. Okay, essentially you have lots and lots of servers, lots of disks, and they're used for all kinds of IT applications. So all kinds of enterprises, okay, because they will run their own applications, they will construct data centers. They will buy a lot of servers, they'll put them in the data centers, and they'll run their applications on it. Okay? And cloud providers will do the same thing, which is why we are talking about this setup. Okay, so enterprises have their own data centers. All internet companies that you know of, Google, Facebook, they have large internet services. They run on data centers. Cloud providers also run their applications on data centers and so on. Okay? And they are used to run all kinds of applications, business applications, web services, batch applications, ML training, all kinds of things that you can think of. They all run on machines that sit somewhere in a data center. Okay? I'm going to show you a picture first before we go back. Okay, this is a picture that shows you what a data center is. So imagine a supermarket. Okay, supermarket has aisles and there are essentially shelves. Okay? Except that on shelves you don't have produce but your servers. Okay, that's exactly what a data center is going to look. Okay, so this is an aisle that you can see. Okay? On both sides you have shelves. On these shelves you have servers that are racked. So these are racks of servers. Okay? And a data center is essentially probably much bigger than a supermarket. It will have hundreds and hundreds of these aisles. Each aisle is going to essentially have racks and racks of servers. Okay? That's the picture you want to keep in mind. Okay? Now, the thing that you will see in a data center, but not necessarily in a supermarket, is these servers are going to generate a lot of heat when they run. Okay? Because all servers, when they run, they generate heat. So you need a lot of cooling in a data center. Okay? So there will be a large amount of cooling infrastructure that is actually used to keep the servers cool so that they don't overheat and burn out. Okay? So it's big cooling infrastructure. Okay? That's one. Okay? In addition to the servers, you'll have cooling infrastructure. The other thing is, of course, the servers are also going to consume a lot of power. Okay? So data centers will have a big power infrastructure that is used to power these servers. Okay? So a lot of electricity gets consumed in running the servers and running the air conditioning that cool the servers. Okay? And if you are running critical applications, you will also have additional backup generators and other forms of redundancy that ensure that even if something fails, like the power goes out, the backup generators take over and the servers keep running and things of that. Okay? So it costs a lot of money, needless to say, to build a large data center. The servers are going to cost money, putting in a lot of money to cool these servers and so on, okay? And power them. Okay, so let me go back and talk a little bit about traditional and modern data centers. So data centers have been around for a long time. Okay? That's how all companies have always run their applications. Okay? The only thing that has changed is the architecture of data center. Okay? The old way was you buy lots of servers, okay? You install OS on them, you run some applications on each server. Okay? After 4 or 5 years, server gets old, you buy new servers and repeat that whole process. Okay? That was the old way. Okay? The new way is you still buy lots of servers, okay? But then you actually run all your applications inside virtual machines. Okay? So each server is going to run a hypervisor. Okay? All your applications are now going to run on virtual machines. Okay? So now, so there was a question earlier, why do you want to do live migration? This will tell you all kinds of reasons you want to do live migration. Maybe a server gets overloaded. Okay? So you can move one or more VMs from that machine to another machine, give it more resources. Maybe you are replacing the machine got old. Okay? Why do you need downtime? You can just move the VM to another machine, continue to run, and then throw out the old server and replace it. Okay? Or you want to do a software install or upgrade the hypervisor. Okay? Maybe you want to patch it. Okay? You don't need to shut down the VM. You can move it somewhere else, patch the hypervisor, and bring it back. Okay? So all kinds of things can be done if you are A, virtualized, and B, you can use things like live migration to deal with how virtual machines are mapped to physical machines. Okay? So all modern data centers, okay, they look exactly like what the picture I showed you, except that every server is actually going to run a hypervisor. And then you can have one or many virtual machines running on each of those physical servers on top of the type. And needless to say, this is mostly going to be type 1 hypervisor. Okay? You're not going to run type 2 in this kind of scenario. They'll all be running some form of type 1 hypervisors. Is that clear? Okay. All right. So let's do a little bit of sort of animation here. So this is virtualization. Here's a rack of servers. Okay? That was the server in one aisle. That's a single server from that rack. You will see that it's running 6 different virtual machines. Okay? That the blue thing is the OS, and there's an application running on there. Okay? So you can run server applications, but interestingly, data centers are also now beginning to run desktop applications. Okay? So you can run what's called a PC on a data center, okay? Which means that your VM is running a desktop operating system. Okay? And it's going to run your desktop applications, and then you simply connect to it from some other machine, okay? And then you can do your work, except that all of your files, etc., not on your local disk, it's somewhere else. Okay? This is also called thin client computing. Okay? Thin client essentially means that the device that's actually used by the end user is a low-end device. It could even be a tablet or some very low-end device, and the actual PC, which means the OS and application, they're running inside a virtual machine somewhere else, and you're simply using a very simple screen application to connect there, so you can see your graphical user interface and so on, and then you're doing all your work this way. Okay? So then you don't actually need to give heavyweight machines to your users. You can give them lightweight machines, or they can connect to their machine from anywhere, because the machine is actually somewhere in a data center. So you simply connect to it and you can do your work. Okay? So that's called a virtual desktop environment. Okay? There are many scenarios where this is used. For example, when you go to a supermarket, okay, many times the cash register is a PC, but that PC is just a thin client. The actual PC may be running somewhere on a server. That way, the data is not actually there, okay, on that machine. It's actually the data is stored securely on some other machine inside a data center. Okay? And there are many other examples like this. So you can use the data center to run server applications, or you can actually use it to run client applications. You can see these are your thin clients that are connecting to the PC on a data center. Okay? 2 types of workloads. There are many more, but that's just examples. Okay? So here is now server virtualization. You can take a physical server. You can run more than one VM on it. We looked at that already. That's called slicing the server into virtual machine. So here is one server. That's your hypervisor. Here you have Windows VM, Linux VM. You can actually map them into here. So you essentially have 2 VMs running. and then maybe one of these VMs get overloaded. So you can see that it grew in size, so you can move the other one and then give the rest of those resources to that orange VM. Okay, so that's using live migration. Okay? So you can do all kinds of things like this. Do it on a LAN, of course. Yeah, just resource allocation. So all of this you will actually see happening in a data center using virtualization. You could not do this with physical machines. Okay? You couldn't simply, if a machine got overloaded, move the process without while it is running. You have to then stop it and move the files and restart it and so on. You don't need to do all that when you're virtualized. Okay? That's an advantage. Okay, so we talked about all of these hypervisors. I'm not going to go into them. Okay, but what I'll talk about is cost. Okay, so running any data center is very expensive. Okay, first you have large capital cost to build the facility. You have to build a large facility. You have to buy lots of racks or servers. That's expensive. Buy large air conditioning units. That's expensive. Okay, a lot of power infrastructure. All of that. So building a data center is expensive. Okay. Running the data center is also expensive, okay, because it's going to take a lot of electricity, okay, to run the servers and so on. Okay. For large data centers, a monthly electricity bill can itself run into millions of dollars, okay, because that's the amount of electricity these large data centers will consume. Okay. So often you want to make sure that your data centers are running very efficiently, okay, so that the operational cost is as low as possible. And the way you are going to measure the efficiency of the data center is through a metric called PUE, power usage effectiveness. Okay? So what is PUE? It's essentially the ratio of the, so that's actually incorrect. So it's the ratio of the total power over IT power. Okay? Total power is the total amount of electricity your data center takes. IT power is the total amount of electricity your servers and your switches are going to take, which means it is not going to include cooling, for example. Okay? So the total electricity will be cooling plus servers plus all of the infrastructure. So it's a ratio of total power to IT power. Okay? The ideal value of PUE is 1, which means that all the electricity is only going to go to power the servers and power your networks. But of course, can't be 1 because you have to spend some electricity to cool the server. But you want to keep that as small as possible because cooling the server is not going to give you anything. You're just giving money to the electric company. Okay, so you want the cooling component to be as small as possible. So the ideal value is 1. Okay? So most of the data centers are typically have PUEs of 1.7 or 1.8, which means it's going to cost you 80 cents of cooling for every dollar that you're spending to power a server. Okay? So effectively, your electricity costs are almost 2x. Whatever you pay to power the server, you pay almost that much to cool that server. Okay? So that's a high cost. Okay? So there's a lot of research into how you are going to reduce the cooling cost of the data center so that the ratio gets closer and closer to 1. Okay? Most of the more state-of-the-art data centers run at 1.1, 1.07. It's getting close to 1, but it can never actually be 1 because there's still some extra cost. Okay? So these are all data centers that companies like Google and Facebook are built because they have very large data sets. So they have to pay a very large amount of money to power their servers and so on. So it's very effective for them to try to optimize the cost of a data center by reducing the PUE as much as possible. Okay? So this pie chart here is just showing you the monthly cost. Okay? So what this is so this red is power for cooling. That's the servers. Okay? So see, so the red plus green is your monthly electricity bill. Okay? That's nearly half the operational cost. The blue is essentially the cost of a server amortized over its 3-year lifetime. So let's say you spend $1,000 for the server. It has a 3-year lifetime, so you divide $1,000 by 36 months. That's a monthly cost of a server over its 3-year lifetime. That's this part. Okay? So that's how much you paid for the hardware to build your data center. This is how much you're paying every month. So it's a large component. Okay? So operating data centers is an expensive business. Okay? So lots of things have been done to reduce PUE. I won't talk about them here, but if you actually go look at papers or even news articles, you'll see that companies like Facebook have tried open air cooling, which means they will put the data center in somewhat cold climates, okay, and then they'll just use outside air to cool the data center. They will just, if the outside air is cold, you can just bring that outside air to cool your machines rather than using an air conditioner. The equivalent of you in the summer, you open the window instead of turning on your air conditioner. Because if it's hot outside, it doesn't work because then hot air is coming. So you have to do this only in colder climate. Okay? So that's one approach. Others have used water-based evaporative cooling. So all kinds of things that reduce the cost of cooling the server. So you don't have to use traditional air conditioning units, which is the standard approach. Okay? So we'll leave it at that, but just want you to know there's some metric called PU. It's a very important metric in the data center world. You want to make that as close to 1 as possible. Okay, that's all that data center operators care about. It reduces their monthly costs. Okay, so that's data centers. We are going to switch to cloud computing. Okay, so what is cloud computing and why is it useful? So now I already said that all these enterprises have to spend a lot of money, okay, running their data centers. Okay, and often you have to essentially decide well in advance of the usage how much money you are going to spend. So for example, you want to build a data center. Okay, you have to think about the data center may have a long lifetime. You have to think about how many servers will I need? Not how many servers do I need today, but how many servers do I need so that 5 years from now I still have enough capacity in my data center. Or you have to think about what is going to be my peak workload, and you have to buy enough servers to serve the peak. Okay? Because if you have less servers than you need, then your applications will get overloaded. Okay? So you have to think well in advance how much capacity you need, and you buy that capacity, even though it may not be used most of the time. And so okay, the average utilization of most data centers, 20 to 30%. Okay? 70% of the capacity is just there for peak periods. Okay? For an e-commerce store application, peak period is Black Friday. For 3 days of the year, you buy capacity and you keep it idle for most of the year. Okay? Because those 3 days of the year, if you don't service your customer, you lose a lot of money. But that's when you sell a lot of stuff. Okay? So you are going to essentially have all this idle capacity sitting, not doing that. Okay? So it's expensive business to run a data center. Okay? So one question you can ask is, rather than building your entire data center, can you rent server capacity? Okay? If you could rent server capacity, then you don't have to pay the cost of building your own data center. Somebody else has done it, and you're just renting servers from them. Okay? So that essentially, the renting model is what has led to this whole area of cloud computing. When cloud computing resources, which means servers and storage, are going to be leased by customer. They're going to be rented. Okay? The rental period could be anything. Okay? You can rent by the hour. You can even now rent by the second if you want. You can rent by years. Okay? There are all kinds of models to rent servers. The point is you don't own the server. You rent a server. Okay? Now, why is this useful? Okay? Because cloud providers allow you to rent on demand. You don't have to rent in advance. So now you could say, okay, I'm an e-commerce provider. I need a lot more capacity in November during Black Friday. March, nobody needs that much capacity. So I'm going to only rent more servers in November. And then the rest of the time I'm renting less. So I can now save money because I'm not buying 1,000 servers and keeping 700 idle just for 1 month of the year. Okay? I'm most of the time going to rent what I need. And when I need more, I just ask for more. The cloud provider has a model that allows you to rent on demand. You can rent and a few seconds later you have a server, because that's how quickly they can provision. That's a big advantage for large enterprises because now they don't have to pay all this cost upfront. Right? So they can essentially optimize their cost by getting resources only when they need those resources. And when you no longer need them, you can return them back to the cloud provider. And so you have what is called a pay-as-you-go billing model. Whatever you use every month, that's what you get billed for. If you don't use resources, you're not getting billed for. Okay? Big advantage. Okay? So So some things that are benefits here are you don't need to create your own IT infrastructure. You can essentially go and rent on demand. All these servers are going to be sitting in some data center. The cloud provider itself built a giant data center and is using them to rent resources to lots of customers. Okay? Each customer is going to get machines that are basically virtual machines, and they can get disk space also with your virtual machine. Okay? So you access all your resources over a network because everything is remote. You pay as you go. Okay? Highly scalable because you can obtain resources on demand. You can spin up VMs, okay? And a few seconds later, you have them ready to go. Okay? It's shared infrastructure, which means that data center is now serving lots of customers. In an enterprise data center, that one enterprise owned all of that data center. There's one customer, which is that enterprise. They build that data center, they own it. In a cloud data center, there may be thousands or hundreds of thousands of customers. Each of them has a different set of resources that they've rented. Okay? So this allows you to have lots of shared economy of scale. Okay? The larger your data center, the more economy of scale you're going to get. So the cloud provider can offer resources much more cheaply than it will cost you to build your own. Okay? So all of these are advantages of cloud computing. Okay? So any questions before I move on? Yes.
Is so cheap that it's not
Okay. Question is cloud resources so cheap that it's not worth having a base level of resources? There are a lot of companies that have all of their applications in the cloud only. They don't have any servers at all. Okay? Because it is a cost to buy your own servers. You have to maintain them, you have to cool them, and you have to essentially upgrade them. All kinds of extra complexity has to be addressed to build your own. So I would not say every enterprise is doing only cloud, but lots of enterprises have decided that's a better model. There are other enterprises that have a mix. They will have their baseline enterprise data centers. Some things are running there, some things are on there. Okay? So for a good use case, why you still want to do your own is data security. Okay? The cloud servers are not your server, they're somebody else's server. Okay? So there's always a problem of you put some sensitive data on the cloud. Okay? There's a security breach because of a cloud provider's fault, but your data is the one that got lost. Okay? So if you have anything that is critical, you want to make sure that's not going to happen. Right? So you have organizations like banks. They don't like to put their data on the cloud. They will have their own data set. Okay? But some other applications that they have, maybe account opening application, that they could run on a cloud server, but not the main banking application. So when you have issues like privacy, security, there are organizations that will still do what you are asking. They will have some of their own data centers, and they will rent some extra capacity on the cloud, maybe to develop applications or do other things. Okay? But this is where a lot of the data center capacity is moving to. As data centers age out, many companies are asking, do we still need our own? Can we just migrate to the cloud? And lots of things that are easily run on the cloud, you just move them to the cloud, but not everything. Okay? UMass is a good example. Right? So Moodle runs on the cloud. A few years ago, Moodle used to run on a server here. Now they have moved it to the cloud. But Spire is still here. Spire actually runs on servers here. They have not moved student records or data off to the cloud yet. Okay? So it's a mix, like many enterprises. Yes, question. PU. Yeah, so question is, do cloud providers have the ability to handle peak loads? And maybe PUE was your question. So cloud providers especially have a strong incentive to build the most efficient data centers, because the more efficient the data center, the more their profit margin. Okay? Because it's a very competitive business. So you can't just raise rates, rental rates, because there are 10 other companies that are offering that rate. So the only thing you can do to make more profits is to reduce your cost, so that the difference between your cost and what you're charging is your profit. Right? So they try to run as efficiently as possible. So every time they build a new data center, they try to see how to make it even more efficient than the previous one. That's one. The second question is the question about peak utilization. So because you are running on shared infrastructure, you can afford to have a lot of capacity that's sitting there, but you don't need capacity that's equal to the sum of everyone's peak capacity. Let's say you have 2 customers, okay, and each of them has an average capacity and a peak capacity. Okay, you can run both of them on a shared infrastructure with fewer servers than the sum of their peak if they are not going to peak at the same time. Okay? If it's an e-commerce provider and maybe there's a sports company, maybe they peak when there are sporting events and the e-commerce company peaks whenever they have sales for their e-commerce store. Okay, so they are peaking at different time. So if you put them on the same shared infrastructure, not all of them are going to come and ask for their peak capacity. So you will get economies of scale. But if you had put each of them in their own data center, you would have to provision each of them for their peak capacity. Okay? So the answer to what you were asking is cloud providers, of course, need to have extra capacity because any of their customers can come and say, I need 500 more servers. And you have to give it to them in a matter of minutes. Right? And you won't have enough capacity that even if lots of them came and asked you for that capacity, you still have that capacity. But it can't be all of them asking for it at the same time. Then you will have to say no, because you didn't build that much capacity. You are assuming that you will have different workloads with different characteristics. And if you have lots of customers, that will actually be the case. Okay, is that clear? All right. So I'm going to talk briefly about this cloud stack in the next 5 minutes, then we will stop and resume on Wednesday. So when we talk about cloud computing, they come in different flavors. Okay? So the 3 things you need to know, or 3 flavors you need to know, one is called infrastructure as a service cloud. Then there's something called a platform as a service cloud, and there's a software as a service cloud. Okay? So the difference, so all of these are called cloud models. All of these essentially involve renting resources from a cloud provider. Okay? And the way they differ is what is it that you're renting from the cloud provider. Okay? In the infrastructure as a service cloud, you are renting bare bone machines. You are asking for a VM. Okay? And then you can install whatever you want in the VM and run whatever application. So your cloud provider is giving you servers, effectively virtual servers or virtual machines, and then you do it all after that. That's called an infrastructure as a service cloud. That's the most basic level of a cloud infrastructure where you get servers and you can also get disks. You can say, I need this much disk, I need these many. Next layer up is called a platform as a service cloud. So in this case, you are essentially renting a platform that's already been configured for your application. Okay? You just write your code and you deploy it on the platform and it will run. Okay? So you don't have to actually get servers. You don't have to install your own operating system. You just write your application and then you install on the platform. And the platform and the cloud provider takes care of deciding how much resources to give to your machine. They charge you by the request. They don't charge you by the server. So if your application starts getting more requests, it's the cloud provider's job to give more resources to your code because it's running in. They are now taking care of provisioning resources for you. You don't need to worry about it. You just write your application in Java or in Python or Node.js, and they have a pre-built platform where you can deploy. Okay? So you don't need to get machines. You don't need to install OS. You don't need to install the runtime. You're just basically getting a runtime to run your code. Okay? So you have a platform. That's a platform as a service cloud. Okay? And the top level is called software as a service cloud, where you get entire pre-packaged applications. Okay? And so you don't actually need to install anything. You are renting a whole stack that includes the server, the platform, and the application. And you just create accounts and give accounts to your user. Okay? Example of this is things like Google Drive, Google Docs, Google Gmail. That's an entire suite. Okay? Office 365 is Microsoft suite. So you can essentially get all of the applications, and they are charging you by the user and by how much resources your user uses. They are not charging by how much servers it takes to run your Google Docs for your enterprise and things of that. Okay? So that's at the very top. So you have Gmail, your business applications like Salesforce, they all run in the application provider's cloud. And you don't need to install anything. You just say, I need to sign up for this service, and then they will just give you an account and charge. Okay. So in all of them, these cases, you are not running anything on your machines because they are all running on the cloud provider's machine. Okay. But what is different is what is it that the cloud provider is giving you. Okay. In an infrastructure as a service, this is also called IaaS. That's an acronym. Okay. This is called PaaS, PaaS, IaaS, PaaS, and SaaS. Okay, so that top one is called SaaS. So depending on which layer you are at, either you are getting bare bone machines, you're renting machines, you're renting a platform, and then you deploy your code, or you're renting entire software stacks. There's pre-configured software, and you can just log in. Okay? So example of SaaS is Moodle that UMass has. That's a software as a service. But somebody's already configured Moodle, and you just go and say, I want to sign up for Moodle, and you just have all of your students get account on it, and then they run Moodle. You don't need to worry about it. Okay? That's an example at the top. You could have also gone and rented a server and then installed an OS, installed Moodle, and done the same thing, but you have to then manage that whole stack. Okay? So depending on what you are trying to do, you can have cloud services at different layers. Okay? Any questions here before we stop? All right, so we'll stop here, continue next time.